All right, so in this next section, transactions, Satoshi gives his definition of what an electronic coin is. And this is a cool idea. So he says, we define an electronic coin as a chain of digital signatures. Each owner transfers the coin to the next by signing a hash of the previous transaction and the public key of the next owner and adding this to the end of the coin. Okay, so this is a cool idea. A payee can verify the signatures to verify the chain of ownership. So Satoshi's saying, instead of having money be an entry in a database, why don't we have money be, say, some value? But also, let's have that money be the record of ownership. So the coin itself, the money itself, if I paid John, okay, what I do is I take a coin and I use my say like a, kind of like a password, which is called a private key, to go ahead and send that to send that to John, and I sign this with my private key, and John can go ahead and verify that I in fact did send that to him. And so the coin is the record of ownership. Now, there's a problem with this. Satoshi points this out. The problem, of course, is that the payee can't verify that one of the owners did not double spend the coin. And then he goes back and says, a common solution to this is to introduce a trusted authority or mint that checks every transaction for double spending. After each transaction, the coin must be returned to the mint to issue a new coin, and only coins issued directly from the mint are trusted not to be double spent. The problem with this solution is that the fate of the entire money system depends on the company running the mint, with every transaction having to go through them, just like a bank. We need a way for the payee to know that the previous owners did not sign any earlier transactions. For purposes, the earliest transaction is the one that counts, so we don't care about later attempts to double spend. The way to confirm the absence of a transaction is to be aware of all transactions. In the mint-based model, the mint was aware of all transactions and decided which arrived first. To accomplish this, without a trusted party, transactions must be publicly announced, and we need a system for participants to agree on a single history of the order in which they were received. The payee needs proof that at the time of each transaction, the majority of nodes agreed that it was the first received. So Satoshi says, hey, look, okay? In this transaction section, Satoshi's saying the problem is that even if we go ahead and have this chain of digital ownership that we create through signing, the problem is we can't be certain that people didn't sign the same two transactions. And so I could pay John and Sally, reverse the payment, quote unquote, or, but then get like a non-reversible service, so good or service. So I can get value without spending money. But he says there is a solution to this, and the solution is that we need a way for the payee to know that the previous owners did not sign any transactions. In order to accomplish this, what we need is for participants to be able to agree on a history. And so in this system, we're going to just look at the first transaction, the first signing event, and that's going to be the one that counts. So if I send a coin to John and then I want to send it to Sally, well, because it happens in the same block time, in the same block time interval, the coin's just going to go to John. It's not going to go to Sally. If I send it to Sally first and then try to send it to John, it would just go to Sally, not to John. So Satoshi's solution to this is to use a timestamp server. Now, the third section of the paper is dedicated to that. What is a timestamp server and how does it work? So basically what we're going to do is we're going to go ahead and use this particular function called a hash function. And a hash function is kind of like hash, like it's just, you've a hash, fuck that. All right, restart. The third section is dedicated to explaining the solution to creating a chronological order of transactions. We do this through a timestamp server. A timestamp server works by taking a hash of a block of items to be timestamped and widely publishing the hash. That's a quote from Satoshi in the paper. He says, the timestamp proves that the data must have existed at that time. Obviously, in order to get the hash, each timestamp includes the previous timestamp in its hash, forming a chain, with each additional timestamp reinforcing the ones before it. So Satoshi's saying that we're going to go ahead and take a block, which we can think of as just a collection of items or a collection of transactional bits of data, transactions. We're going to take that and we're going to go ahead and put all this data into a hash, and we're going to get a hash code from that. Now, that hash code is going to be distributed widely, or we're going to publish the hash to everyone in the network. So everyone in the network can see, hey, this hash was created at this time. When we do that, we're verifying that the transactions must have existed at that time in order to get the hash. The reason that this is can be like a valid thing is because a hash function only allows you to like it's very difficult. A hash function is what we would call a one-to-one function. A hash function is what we would call a trapdoor function. So a trapdoor function takes some input and it gives you an output, but it's very quick to create an output from an input, to take random transaction data and to get a unique code for that data. It's very hard to tease out what the data was to create the unique code. And because of this property of hash functions, this allows us to be probabilistically certain that the transactions did in fact happen in this particular order. And the probability is very high. So this is Satoshi's solution.